Dear friends, welcome to my video on quantum computer hardware explained. Kindly click on the CC button for subtitles. Quantum computing is a revolutionary technology poised to change how we solve problems, process data, and perform computations. But behind the scenes, quantum computers require a radically different hardware setup compared to traditional computers. We'll explore the essential components of quantum computer hardware, how they function, and why they matter for the future of computing. Quantum bits, qubits, the building blocks. In classical computers, data is processed in bits, represented as zeros or ones. However, quantum computers rely on qubits, which can exist in both 0 and 1 simultaneously thanks to the phenomenon of superposition. This dual-state capability allows quantum computers to process complex computations much faster than classical computers. Qubits are typically created using several technologies. Superconducting qubits. These are circuits that can carry current without resistance at extremely low temperatures. Trapped ion qubits. Atoms are suspended in a vacuum and manipulated with lasers to perform computations. Photon-based qubits. Using particles of light, photons, quantum information is encoded and transmitted over long distances. Topological qubits. This method, still in experimental phases, relies on quasiparticles to store information in a stable form. Each type of qubit has its own challenges in terms of stability and error correction, which makes it a key area of ongoing research. Quantum gates, manipulating qubits. In quantum computing, quantum gates are the equivalent of classical logic gates, but they operate on qubits. These gates manipulate the qubits through operations like rotation and entanglement. Unlike classical gates, which handle individual bits, quantum gates can operate on multiple qubits simultaneously, thanks to entanglement, a quantum phenomenon where qubits become interconnected and the state of one qubit can depend on another. For example, a Hadamard gate can put a qubit in a superposition state, while CNOT gates are used to entangle qubits, making them interact in unique ways that allow quantum computers to perform more powerful computations. Quantum processor, quantum processing unit, QPU. The quantum processor, also known as the quantum processing unit, QPU, is the heart of the quantum computer. The QPU contains the qubits and quantum gates, and it operates at near absolute zero temperatures to maintain quantum coherence. Most quantum processors are housed in cryogenic environments to reduce noise and increase stability. Companies like IBM, Google, and Intel are pioneering quantum processors, each with their own designs and capabilities. IBM's QPU, for instance, relies on superconducting qubits, while Google's Sycamore processor has made headlines for achieving quantum supremacy, where it solved a problem that classical computers would take millennia to compute. Quantum error correction, ensuring accuracy. One of the biggest challenges in quantum computing is error correction. Because qubits are extremely sensitive to their environment, they are prone to errors from factors like temperature fluctuations and electromagnetic radiation. Quantum error correction codes are used to detect and correct these errors. However, this is an area that still needs significant development as maintaining quantum coherence for long periods is difficult. Control systems, managing the quantum computer. Quantum computers require control systems to manage and execute computations. These systems use classical computers to send instructions and retrieve results from the quantum processor. The control systems must be incredibly fast and precise to manipulate qubits accurately without introducing errors. Cooling systems, maintaining quantum stability. Since qubits are highly sensitive, quantum computers must be kept in an environment close to absolute zero. This is achieved through sophisticated cooling systems, often using dilution refrigerators, to maintain the qubit stability. Any slight change in temperature can cause qubits to lose coherence and introduce errors, making cooling an essential component of quantum computer hardware. Conclusion: quantum computing represents the next frontier of technology, and its hardware is the foundation that makes it all possible. From qubits to quantum gates, and the intricate cooling systems required, understanding quantum computer hardware is key to unlocking the immense potential of this revolutionary computing paradigm. While we're still in the early stages of development, ongoing advancements in hardware are paving the way for quantum computers to tackle problems that classical computers could never solve. Thank you for watching my video. Kindly subscribe to my YouTube channel and give a thumbs up. Thanks for your support.